Okay, number 39. So number 39 says a heat engine takes 0.350 mole of a diatomic ideal gas around the cycles shown in the diagram here. So I'm going to draw the cycle. So V, P, and it looks like this one, going from 1 to 2 to 3, those are states, and it's going clockwise. That T1 is 300K, T2 is 600K, T3 is 455K, and this particular process from 2 to 3 is adiabatic. And the pressure here given is 1 atmosphere. There's no volume given here, no volume given here. So I'm just going to mark it as A1, V1 and V3 here. Okay, so they're saying is that this one, of course, is isochloric, adiabatic. From 3 to 1 is isobaric. And the isobaric is a constant pressure of 1 atmosphere. The gamma for diatomic is given as 1.40. Even if they didn't give you that, you should know that when they say diatomic ideal gas, right away in your mind you should come up with gamma being 1.40. So anyways, here they ask find the pressure and volume at all 3 points. So find the pressure and volume of all 3 points. Okay, so I'm going to find out P1, P2, P3, and V1, V2, P3, and so on. Now, if you look at this question, you are given the pressure and time of, pressure and temperature of this one and that one, because the pressure is always 1. So that means if you know 2 of the 3 things, P, V, T, if you know any of the 2 of those P, V, or T, then you automatically know the third one, the missing one. So in this case, you know P and T, so you should be able to figure out V1. And once you know V1 and T2, then you should be able to figure out P2. And here, you know pressure being the same. So you know P3 is 1 atmosphere, and T3 is 455, so you can also figure out V3. So once you know all the P's and V's and pressure and temperature of all corners, then pretty much you can answer any question on work done or any question on heat, input or output. Alright, so we will go through what I just said before. Let's figure out V1, because I have temperature and pressure at 1. So at 1, PV equals nRT, so in this case 111. And V1 therefore is nRT1 over P1. And given number of moles already, n was given as 0.350 moles. Now, sometimes, even if they did not give you the moles, if the question they are asking, for example, is the efficiency, then you can just assume n is 1 mole and work out the whole question as if n was 1. And then at the end, figure out the efficiency of the engine without, answering some of the exact volumes or so on, because they will all have an n associated with it. But in terms of efficiency, n cancels. Okay, anyways, that's the side point. So in this case, when n is given to you, then lug it around. So 0.350 times R, 8.31. T is 300, so everything is in P. Okay, now you cannot use 1 atmosphere if you use 8.31 because that is MKS unit. So change that to 101.3 kilopascal. Okay, so rewrite this one as Pascal, for example. And then this will be 101.3 times 10 to the 3 Pascal. So if you figure out this number, 0.35 times 8.31 times 300 divided by 101.3 kilopascal. So I get a volume of 8.61 times 10 to the negative 3. This will have to be cubic meter now. 8.61 times 10 to the negative 3 cubic meter. So that's a V1. And of course V2 will be the same. P1 we already know is 1 atmosphere. So P1 is 1 atmosphere. And V1 is 8.61 times 10 to the negative 3 cubic meter. Okay, so at 2, well, we already know V now at 2. So PV2 equals nRT2. T2 is 600, and V2 is same as V1. So we can figure out P2, which is nRT2 over V2. V2, by the way, is the same as V1, which is 8.61 times 10 to the negative 3 cubic meter. So 0.350, 8.31. T2 is 600K, divided by V2 is 8.61 times 10 to the negative 3. So I get a pressure P2 as 0.350 times 8.31 times 600. I get 2.03 times 10 to the 5 Pascal. 2.03 times 10 to the 5 Pascal. Okay, so P1, P2, 3. At this point, I don't know the volume, but I know the pressure, and I know the temperature. So to figure out V3 then is nRT3 over P3. N is 0.50, 8.31. T3 is 455 divided by P3, which is isobaric, so it's same as 101.3 kilopascal. So I get 0.35 times 8.31 times 455 over 101.3 kilopascal. I get a volume of 0.0131, which is 1.31 times 10 to the negative 2 cubic meter. 1.31 times 10 to the negative 2 cubic meters. So here are the answers: P1 V1, P2 V2, and P3, which is P3, which is also 101.3 times 10 to 3 Pascal, which is same as 1 atmosphere, and V3, which is this number. Okay, so we answered part A already. Part A is find the pressure and volume of AP at 1, 2, and 3. And part B says calculate the heat, work, and delta U of each one of the 3 processes. For that, the best thing to do is to write yourself a little table here. So the table will look somewhat like Q equals to delta U plus W, such a table. Okay, and this will be the process of 1 to 2, 2 to 3, 3 to 1, and then this will be the sum, the total, or net, if you like. Okay, from 1 to 2 is isochloric, so there is no work for isochloric. Okay, and therefore the work or the internal energy change is NCV delta T. So let's figure out NCV delta T. N is 0.350. CV, well, if CV for diatomic ideal gas, okay, according to the table, normally they will give you what the CV and CR and gamma will be, or at least what CV is. For diatomic gas, CV is 5½ R. For monatomic, CV is 3½ R. Okay, this is monatomic, and this is diatomic, so we have to use this one. And therefore, CV is 5½ or 2.5 times 8.31, and delta U in 1 to 2 is change in temperature, which is 600 minus 300, so it's 300. So that would be the delta U, and if you calculate that, 0.350 times 2.5 times 8.31 times 300, I get 2181 joule. So that means change in internal energy is 2181 joule, and for 1 to 2, therefore the heat will be 2181 joule to put in. So that is Q in, okay, positive. And then from 2 to 3 is adiabatic, which means heat cannot, it has to be 0, no heat change. But the change in internal energy is still NCV delta T. But in this case, you will have to be from 600 down to 455, or shall we say it is the NCV, so 0.350, 2.5, 8.3, but T3 minus T2 is 455 minus 600. So 455 minus 600, that is the final temperature minus initial temperature. So we're going to get a negative number, 0.350 times 2.5 times 8.31, and times 455 minus 600. So we are going to get a change of 1054 joule. That is a drop in internal energy. But of course, the work is the opposite of that, and it should be positive because it is going from left to right, and the area underneath the curve when it's going from left to right is always positive, so it's positive 1054. And then from 3 to 1 is isobaric. Isobaric, okay. Again, the change in internal energy is again the same way, except in this case, well, let me mark this one as 2 to 3. 2 to 3, and this is 1 to 2. So this will be 3 to 1. 3 to 1. So final minus initial. So again, 0.35, 2.5, 8.31, and then 300 minus 455. So I get 0.350 times 2.5 times 8.31 times bracket 300 minus 455. So I'm going to get negative 1127 joule. So that is a drop of negative 1127 joules. But what about the work done? Well, work done for isobaric is either you use nRT, okay, nR delta T, I mean, which is change in temperature is still negative 155, okay. So N is 0.35, R is 8.31, T is a drop off from 300 minus 455. So the work is negative 451. Okay, so that is work, or you can use the difference in volume times the pressure of this. You should get the same answer. For example, if I take, just to double check, V3, we figured was this number. So V3 minus V1 is the difference in volume, 1.31 to the negative 2, minus V1, which we figured was 8.61 to the negative 3. So we now have a difference in volume, and then multiplied by 101. That's the pressure, times 101.3 kilopascal. I get 455 joules. That's about round off error. So that's about right. And of course, I should have used V1 minus V2, therefore end up with a negative work. But anyways, it's the number matches to this number. So, and the Q would be the sum of the two. So if I just add these two up, 1127 plus 451, so it would be negative 157A joule. Now, for isobaric, we could also easily use NCP delta T, okay, for isobaric only. But, you know, N is 0.35. CP is actually R higher than CV. Now, CV, we said for diatomic is 5 halves. So for CP is actually 7 halves. So times 7 half of R. Delta T is 155. So times 155. Oops. So 0.35 times 3.5 R times 155. I get a work of 1578. Okay. So that matches this number. So that's just a double check. Okay, they're all correct. Now here's another double check. If you add these up, these two columns should be the same and this should be 0. So internal energy in a cycle is always 0. So let's just add these up. 1054 and minus 1127. Well, it's actually exactly 0. So this is exact. So that's correct. And then add these two up. 1054 minus 451, 603. Now this better be 603. Let's see. 2181 minus 1578, 603. Exactly, because these two numbers must match. If they don't match, then you made some mistakes. So to answer that last question, this question part B says calculate the Q, the W, and delta U for each one of the 3 processes. So here's the Q, U, delta V. Okay, and then find the net work done by the gas in the cycle. Well, the net work is right here. Okay, that's the net work, 603. And find the net heat. Well, that's right here, 603. They better be the same. So the net heat into the engine in one cycle, and that's positive number, so is flowing into the engine. And then part E, the question is, what is the thermal efficiency of the engine? Well, thermal efficiency of the engine, as we know, is efficiency is the work done divided by the Q in. Okay, if you look at the Q positive is only 2181 is positive. The work done is 603, so we divide 603 network by the heat input 2181, you get 27.6%. Okay, so that is the efficiency of the engine. However, if you want to compare that with the efficiency of a Carnot cycle engine, operating at the temperature of T1 and T2, that means these two. Okay, but we know that the efficiency of the Carnot engine is 1 minus T, the lower one, which is 300, over the higher one, which is 600. So that is 1 minus 300 over 600, which is just 0.5, which is 50%. No, so that would be the Carnot engine's efficiency. So if we compare the answer, let's say P1, which is a 1 atmosphere, V1 is 8.62, okay, 8.62 times 10 to the 3, okay, there's one off, doesn't matter. P2, this one should be twice the 101.3, is that right? Kilopascal, oh yeah, that's right. So this is 1 atmosphere, 2 atmosphere, or 202.6, or 2.02 times 10 to the 5th, like so. So that's correct. And 8.62, yeah, same thing, cubic meter. And P3 is 1, which is 1 atmosphere. And V3 is 1.31 times 10 to the negative 2, so correct. So these are all correct. Correct. And then for the table, 2183, they got 2183 for then, and then 2183, and then 0, okay. And then you have 0, and then you have negative 1055, that's their answer, 1055, okay. And it's negative 1579, negative 1128, negative 451, but they add with 604 and minus 603, so it's probably just rounding error. The efficiency is 27.7%, I got 27.6, and Carnot is 50%, so everything's correct. So that's number 39. Okay, number 41. Number 41 says, what is the thermal efficiency of an engine that takes n moles of diatomic, so n moles of diatomic ideal gas, okay? Well, if it's diatomic ideal gas, so you should remember that this is pretty much is 1.40, and that CV is 5 over 2R, okay, that's diatomic, 5 over 2R, Now, of the diagram that they show you here, and basically is it's just a rectangle where it goes like so, from 1, 2, 3, 4, 1, 2, 3, 4 being the states, and then the volume here is V1 or the V0, and this is twice as big a V, but the pressure here is P0, and this will be twice as big as this one. So you basically know all the volumes and pressures given that they are in ratio with each other, but they're not asking for you know, specifically what the temperature or at any of the corners or heat or internal energy. They're just asking for the efficiency. What is the thermal efficiency? Okay, efficiency we know is the work done divided by the heat going in. Okay, so we need to therefore find the net work and all the positive heat that goes in. Okay, so we have to basically set up that table, which I call from 1 to 2, and 2 to 3, 3 to 4, sorry, 3 to 4, yeah, and then 4 to 1. Okay, we need to set up the heat, and then the change in internal, and then of course the work. But we really don't care about the internal in this case. Okay, so now this is isochoric from 1 to 2, but we can figure out the temperature. For example, the temperature T1 is P0V0 over NR, right? PV over NR. So T1 is just P0 over V0, T1. What about at T2? Well, T2 should be 2P0, this guy, V0 still, okay, over NR. So, but this part is already, we know is T1, so this is 2T1. So T2 is actually twice the temperature of T1. Well, let's figure out what, well, let's say what T3 is. T3 is P, which is 2P0, V is 2V0 over NR, which looks like 4P0V0, or 4T1 then, okay? And T4, which is P, pressure P0, volume is 2V0 over NR, which is twice T1. So we can express all the temperature in terms of T1. And that is, if this is T1, T2 is twice the T1 here, T3 is 4 times T1 here, and T4 is 2 times T1 here, okay? Oh, it looks like from here to here is actually isothermal. Anyways, so we now know the temperature at each point. Okay, now the net work here, I'm not sure if you need to figure out each individually, because all you need to know is what's the area here. But the area here is very easy. It's the difference in pressure, which is a single P0, and difference in volume, which is single V0. So the work done is simply P0 times V0, okay? Because this distance is P0, and this distance is V0, because 2V0 minus V0 is V0. So this will be the work done, okay? This will be the work done. Now what about heat that goes in? Well, heat goes in for 1 to 2 is NCV delta T, okay? Because there's no work. From 1 to 2 and 3 to 4 there's no work. That's because it's isochoric. Isochoric have no work. So all the heat is from the change in heat, which is NCV delta T, or you can say N 5/2 R delta T. Okay? So therefore the heat of the 1 to 2 is actually same as the internal energy increase. It's actually 5/2 N R. Now delta T is change, which is 2T1 over T1, right? That's a change, which is 1T1. So just T1 then. So this one is 5/2 R or NR or RN T1. Okay, that's heat. That's the heat going in, and this is the same here, 5/2 RN T1. Okay, and similarly, from here to here, it will be 2T minus 4T. Well, that would be negative 2T now. So it's not just a single increase in T. It's actually dropping of 2T. So from isochoric from 3 to 4, it will be 5/2 Rn, but instead of increasing by a single T1, it will be negative 2T1 because it's a drop. So that will be negative 2T1, okay? And this will be 5/2 Rn, negative 2T1. Okay, so from 2 to 3, the internal energy is still 5/2 Rn, okay? Change in temperature is 2T1, so 2T1. And here is change in temperature is 1T1, but minus. So that will be negative 5/2 Rn, or I mean negative T1, because it drops from 2T1 to T1, so negative. So if you look at if I add these up, everybody has 5 half hour n here. Everybody has 5 half hour n. So it's really T1, 2 T1, those 3 T1 so far, minus 2 T1, minus 1 T1. So they all add up to 0, which is what we expected. But the work done from here, from 2 to 3, is nR delta T. Okay, for isobaric is just nR delta T for work done. So nR delta T, in this case, increase of 2 T1. So from 2 to 3, increase of 2 T1. So 2 T1. And from here to here, though, is a drop of 1 T1. So the work would be nR negative T1, a drop of T1. So if you add these up, you have nR 1 T1, because 2 T1 minus T1 is 1 T1. So this is the total net work done. And what about the net? Well, for 2 to 3, from 2 to 3, well, you either add these two up, which is, let's see. Okay, let's cancel this one now. So 5 RN T1, 2 RN T1. So 7 RN T1, 7 RN T1, right? So 2 cancel 2, 5 RN T1, 2 RN T1, so 7 RN T1. Similarly here, now, okay, here's going to be a fraction. So this is 2.5, negative 2.5 RN T1, negative RN T1. So negative 1, negative 2.5, negative 3.5. So negative 3.5 is same as negative 7 half RN T1, okay? So if you want to calculate the efficiency, which is simply the total work, which is nRT1, divided by the total heat, positive, that's put in. Well, these two are negative, okay? From 3 to 4 is negative heat, and this is also negative, so the only positive are these two. So you have to add these two up. That's 2.5, and this is 7. 2.5 plus 7 is 9.5, so 9.5 nRT1, nRT1. So these cancel, so just 1 over 9.5. Therefore, is 10.5%. So in question 41, is 10.5% exactly right. Okay, so that's how you do it. You notice that I just used n here without plugging in any number. That's because I know that eventually they're all going to cancel anyways. So there's no point in plugging all the number, calculating, and potentially getting wrong key enter in the calculator. And if you get one number wrong, you screw up with the rest. So here I kept the n and r and T1 because everything is kind of based on T1. It's actually easier to just use letters instead of keep punching in calculator and rounding off errors. So anyways, so I end up with 10.5 in this question. And that's how you do it. Number 43, I've written out the table. Now read the question. Thermodynamic processes for a refrigerator. A refrigerator operates on the cycle shown in this diagram here. The compression, which is from D to A, and the expansions from B to C are adiabatic. So these two are adiabatic. Now the temperature, pressure, and volume of the coolant in each of the 4 states, A, B, C, D, are given in this table. Now these values are at each corner, or at each state. Now the question A is, in each cycle, how much heat is taken from inside the refrigerator into the coolant while the coolant is in the evaporator? So in other words, how much heat is entering into the system during C to D cycle? Okay, so in that case, we need to look at a few things. One is what is the internal energy change and what is the work done. So during C to D, it is isobaric. So if it is isobaric, well, we need to know two things. One is how much heat, which is the amount of change in internal energy plus the amount of work done, and that would be the heat provided. So first, let's figure out the amount of change in internal energy. That's easy because they have provided already the amount of internal energy given, and which is basically from C to D. So therefore, I will use the internal energy at D minus internal energy at C. Okay, so D internal energy is 1657, and C is 1005. Now these are kilojoules. So I basically get 652 kilojoules. Okay, I'm just going to write it in joules instead. Okay, but these are in kilojoules. Okay, so that is the change in internal energy. And then what about the work done? The work done is P delta V for any isobaric, which is the pressure, which is from C to D is always 363, Now that's kilopascal, so times 10 to the 3. And volume will be VD minus VC. Excuse me. VD minus VC, which will be this one minus this one. So 0.4513 minus 0.2202 in cubic meter, so that should be fine. So the work done, if you calculate it that way, will simply be, let's see, 83889.3 joules. Okay, so then the total heat, in this case, will be heat in or heat cold going in, should be the sum of the two, and that is 65,2000 plus 83,889. However, let's make sure the signs are correct. So if I add these up, I should have 735,889 joules. So that is the amount of heat going into the system. 735,889 joules. And then, that's part A. So how much heat is taken from inside the refrigerator into the coolant while the coolant is the evaporator. So that is from C to D. Part B says, in each cycle, how much heat is exhausted from the coolant into the air outside the refrigerator while the coolant is in condenser. Well, you probably should figure out it has to be in the condenser because these two are adiabatic. There's no way that heat can be exchanged. So it has to be in the condenser. So the way, therefore, is find out what is Q high, which is the Q between A to B, from A to B, which is change in internal heat from A to B, plus the work done, in this case, VB minus VA. Okay. Now you can see that VB is actually smaller than VA, so this will actually be a negative, which means work is done from the environment to the system. Anyways, let's figure out delta UAB. So it's UB minus UA. UB minus UA. So 1171 minus 1969, and then P, which is 23. These are in kilo, and then P, which is 2305 kilo Pascal, times the change in volume, which is VB, is 00946 minus 00682. So if you calculate the numbers here, you're going to get a negative, this part is a negative 798,000, and this part is going to be a negative 135,396. So for a total of negative 933,396 joules. Alright, okay, so that is the heat out. So that is part B. It should be negative, meaning that it is heat leaving the system to the environment, as we expect for refrigerators. And part C, in each cycle, how much work is done by the motor that operates the compressor. Well, work done is the area here, okay? And since there's no change in heat here, so another way to figure out the work is it must be the high heat minus the low heat coming in, because that's the rest of the work going into the system. Because if you recall, for refrigerator, is this relationship. So W is merely the change of high heat minus low heat. Now, but in absolute value though, because okay, so let's see. The absolute value of this one, C is high heat is 933,396 minus the low heat of 935,889 for a difference of 197506. Okay, rounding off error here somewhere. Let's double check. 933,396 minus 735,889. Okay, probably rounding off error. Maybe we're 7 here instead. Okay, so that is the amount of work done, and that will be going into the system rather than system. So if you just find out the value, it should be negative, which means that the environment is doing work to the system rather than the other way around. So in answering this question, in each cycle, how much work is done by the motor that operates? Okay, since they already stated by the motor, so you don't have to say negative. Just say 197507 joules, or round it off to 3 sig figs. And D, calculate the efficiency of performance of the refrigerator. Well, the efficient performance is how much cold heat is taken out with the work that you've done. Well, which is basically just this divided by that. Okay, so 933,396 divided by the work done, which is this guy, oh, this is not the heat. That's 7358889 divided by 19507. 197507. So 735889. So I get a number of 3.73. 3.73 is the coefficient of performance. So this is part. Okay, this is part C, and this is part D. So let's see if the answer is correct for number 43. The answer is for part A, 7.36 times 10 to the 5th, 7.36 times 10 to the 5th. So in this case, 7.36 times 10 to the 5th joules. Okay, so B, that should be right if you round it to 3 which you should. And then part B is 9.33 times 10 to the 5th, 9.33. Okay, 9.33. Okay, it's positive because so it should be negative, but since they're just saying heat exhausted, so you don't have to say negative. 9.33 times 10 to the 5th joules. So that's the official answer. And then part C is 1.98. That is work done 10 to the 5th. So that is this number 1.98 times 10 to the 5th. Okay, so that looks correct. And then the performance efficiency, coefficient of performance 3.73. That's exactly right. So that's how you do this question number 43.